Obviously, guys, we have Sarah also on our team. She's not here. She's talking about problem, but I will represent it here. And we have Zahra Ashir. Next slide. That's a Huntley Power Station waste to energy. So, do you know that the New Zealand imports 575 tons of plastic on 2018? That was the latest data we got. That's equivalent to 7,200 Airbus Boeing 737-800 airplane. That's about the one that takes off the big planes. 7,200 of it. Imagine how big it is. And if you want it in human numbers, it's about 9 million person. That's double New Zealand. Let's continue. In one year only. That goes to landfill. Just buried. So the contents of the project will be introduction to project, problem, solution, and our recommendation. The problem is that Huntley Power Station is one of the biggest carbon emission source in New Zealand. It represents 5% of the carbon emissions in New Zealand. And on the other hand, we have plastic waste, which represents 575,000 tons to be sent in landfills. And plastic statistics. We had a big issue finding statistics. Sarah contacted EnviroWest, Plastic Organized, Hamilton Council, Auckland Council, Wellington Council, Hamilton Waste Management. None of them had any information. We found some information with the Ministry of Environment that had 2018, because even a research by Auckland and Wellington researchers, a big one, 100 pages one, stated at the beginning that New Zealand have a big gap in information about how much plastic they have. They just know how much mixed one they have. On 2018, they have put all their effort to find how much do they have. So they give us percentages. LDPE to be 31%, HDPE to be 27%, and things like that. So we build our assumptions based on that. We go to the next page. We made an assumption that the range of plastic waste in New Zealand would be between 100,000 and 1,000 tons, or 1 million tons. So it would be 100% between that number. But how much, we're not sure. But in 2018, it was 575,000. We have the percentages that they got by then. 7% for PET, 26% for HDPE, 31% for LDPE, and PP is 18%, PS is 40%, and 12% for PVC, and 3% for other plastic waste. We're not going to use them all, but at least we need to know how much we have. Next page. This is showing the quantity of each type of plastic, and we're assuming that yearly it goes in a linear increase, because the pollution increases, plastic use increases, so the plastic waste will increase. And now Zahra opinion.
So, for this discussion, we are discussing about the best method in converting the plastic waste into liquid oil by using a chemical process called pyrolysis. Pyrolysis is the organic process of degradation of material when subjected to heat in absence of oxygen. But before doing pyrolysis, we need to do a pre-treatment process for the plastic waste we get it from the waste management. So we need to do the sorting method for the plastic waste. So we have it's divided to manual, automatic, and combined. The manual one we don't consider to do it because it's need it will take long times and it needs intensive labor, and it's have bad working environment. So for that we just considered the solution we will do it with the sorting method to have a combined to automatic method. So we are considering to do the dry sorting of the doing the X-ray and infrared rays. So this the concept of this method is by exposing the plastic waste to these rays. So we are considering to not have the PVC in the plastic to do the pyrolysis because it's will producing HCl acid, which owns all the process. So for that we need to do two sorting methods. The first one to remove the PVC, the second one to sort the old plastic waste. The second one we can use the dry. We are considering more about the dry sorting more than the wet sorting because it's put it's too complex, like the wet sorting, we are not considering to do the chemical sorting, as we will do the pyrolysis as a solution. Next slide. So the pyrolysis operation condition. So there is some factors controls our the pyrolysis process. So it can be summarized by the temperature, operation pressure, residence time, reactor type, catalyst type, and type and rate of pressurizing gas. So in temperature, so mostly it's the main condition that control the pyrolysis process. So in temperature, if the condition is almost effect on the final product we want. So we are considered to have liquid oils. So if we prefer the liquid oils, so the prefers the temperature range preferred for it, like 300 to 500 degree. But if we prefer the final product would be the gases or mixture, we will use we will run the pyrolysis at temperature more than 500 degree. So here is a table that summarizes the range of the thermal degradation for each type of plastic. The thermal degradation is the temperature when the plastic lose molecular weight. So that's for all the plastic types. And the other operation condition is the pressure. Pressure is a factor that depending also on the temperature. So at high pressure will increase the use of non-condensable gases and will decrease the use of liquid product. So we the research we have read it. It's all conducted at atmospheric pressure. So and we will have the liquid at temperature less at range 300 and 500 degree. Right? So residence time. The residence time definition is differ from the in fast pyrolysis and in slow pyrolysis. So in fast pyrolysis, it's referring to contact time of the plastic on the hot surface throughout the reactor. But in slow pyrolysis, it's referred to the duration, the duration from time of heat the plastic start to heat it on the time when the products are removed. And also for residence time, the research is conducted before. It's not considered as an end condition, but it also has effect on the final product of the pyrolysis. So at longer residence time, it's favored for product conversion of primary products. So it will convert the plastic at that time. So and will producing more stable products like light molecular weight hydrocarbon and non-condensable plastic. But in long residence time and slow pyrolysis will encourage the carbonization process and produce more charge and the product. So now okay. So in this table, it's like summarize the process condition to gain the targeted product. So as you see the process for the slow carbonization, slow pyrolysis, and here is the residence times and temperature were predicted for this process and what we started products are. Now I will
I'm going to talk about the reactor types. First of all, bit batch and semi-batch reactor types. Reactor is where the reaction happens. So basically, it's a closed system that carry no outflow or inflow products, reagents within it. So you just simply put everything inside and it's closed. You can't add any products. You can't add anything inside. Just once you put everything, that's it. The problem with batch and semi-batch that it's only good in laboratory scale. When they tried it in industrial scale, it failed so badly. Fixed and fluidized bed catalysts are mostly in packed form and packed and stacked non-static bed. Remember when I say stack, it means like boxes. Imagine boxes over boxes. So mainly the plastics used there needs to be on the same shape. So that was the only problem with fixed and fluidized bed. To overcome that, they need to add the catalyst in the middle when all the plastics are liquefied already. The positive thing about the fixed and fluidized bed is that you have those two holes that you can add and add and add, so that it's a plastic or catalyst in the middle. Because as I said, you need to liquefy the plastic until 400 degrees, and then you keep adding the catalyst. And the conical spouted bed was made to solve this problem. The problem with fixed and fluidized bed. They made it a bit conical shaped in the bottom, but the same problem is that it had lower yields, and the same thing as the batch and semi-batch, it didn't show that much big, the big potential that they've done in the laboratory. When they did it in industrial, it didn't show much. But that's in terms of pyrolysis. But in terms of other chemical or other processes, it showed the potential that they needed. The newest technology is the microresistor technology. It's the most interesting current one. When they put just a carbon absorbent and they add it to the plastic itself, it does take less energy, it does take less time to do, and gives the biggest yield. The only problem is just 1 year or 2 years ago that they started developing it. So maybe future recommendation to start with this one, but for now we'll stick with the fixed and fluidized bed and evolve it. This table shows previously done experiment on 2016 on each reactor type and the yields given by each one of them for each type of plastics. As you can see, there is no PVC in the table. This is because this is the only PVC. The PVC is there because we won't use it because it will exert HCl in the process of pyrolysis. HCl, as we all know, is an acid. So if you have acid among your oil, it will ruin everything. So cross the PVC. If you look at the top of the table, you have PET using the fixed bed, but the problem is that you have the yield of oil about 23%, which is useless. Because if you're losing 70% or 80% of your plastic oil, you're not getting only 20% liquid oil. There's no point to doing that. On the other hand, you have HDPE, which gives you around 80%, 91% sometimes, and you have PS, which gives you 96 or 97%. That's with different reactors and different catalysts. The best one, as we found, was the fixed and fluidized bed, but we'll use different catalysts. We'll go this one next. Slide. Now we'll talk about the catalysts. Catalysts are mainly made to speed up the reaction speed and make sure that the yield will be as maximum as possible. And as we know, there is activation energy needed for each chemical reaction. For those ones, for the pyrolysis, it is very huge. Using the catalyst would lower it. Currently, or the best values they got, using the FZ catalyst, this gives the best outcomes. Alumina silica was used in some part of time, but it didn't show that much of stabilized values with every one of them. It shows the good values with some of them and low with others. Zeolite has been used commonly, but it's not proven yet. It was just a new one. But the latest one was on December 2020, as I remember, by Singapore. They used vanadium and showed them a very good potential. So we're thinking about using vanadium with fluidized gas bed. Next one. Now type and rate of fluidizing gas. In the fluidizing bed, there is a gas that goes in, which it might be nitrogen, helium, argon, ethylene, propylene, or maybe hydrogen itself. Those ones, they differ and they change their activity level based on the molecular weight of each one, of course. So as you can see here, the hydrogen, all those carrier gases will be there. They have different molecular weights, and the higher going the molecular weight, the less is the conductive productivity. This means that the best one we could use is hydrogen, especially that it gives us a lot of olefins and less coke yield, because we don't want coke yield at all. Next one. This is the CO2 emission calculations. As you know, the main thing is to get rid of the CO2 emissions. Here we got the steam turbine. Huntley Power Station has 2 steam turbines that run by coal. So we added them up to have 500 megawatts. Efficiency is 33%, and that's the thermal energy. The percentage is 50% because we're calculating for one of them. So it's basically one of them is 250. So that's why we divide by 2. We have this thermal energy, we have the coal, we got information from Mark Clay. He got it from Genesis in Environmental Sciences. And that's how we got the CO2 emissions, about 2,920,000 tons per year. That's how much they have. And after adding our project, or after applying pyrolysis and turning plastic waste into liquid oil, we have 1,150,000 emissions with pyrolysis oil. That's how much it will save. So the new one, it will be 1,100,000, or 30% of the coal will be used only. We reduce the amount of coal, but the amount of plastic that Tunisians have is not sufficient enough to replace all the coal. So we only replace about 70% of it. Based on that, we have CO2 emissions of Huntley Power Station as a whole will be 72% less. Next slide. Not everyone understands the numbers, so if we imagine that CO2 emissions in Huntley Power Station is a piece of pizza, the remaining will be, after applying pyrolysis, is a quarter. So this one and this one and this one will be out of, because we got rid of it. And now Zahra will continue.
So our recommendation for Huntley Power Station will be to have a third party doing the sorting methods and also doing the pyrolysis process and then deliver the pyrolytic oil to them, or they can create their own sorting plastic plant and pyrolysis plant, but it will be more costly for them. And